Let's begin. So we're going to start on the third topic in this series of lectures. The course is going to go through a series of topics. And as we go through the semester, the topics will initially take more time and then finally to begin taking lesser and lesser time because we will be a bit hurried. But this one is going to be a series of 5 lectures on recurrent neural networks and various formalisms. So the problem is here is that of trying to model series. In many situations, we find ourselves in many problems, we find ourselves in a situation where we have to analyze an entire series of incoming data in order to take one or more decisions. For example, speech recognition. So if you were to do something like wake-up word recognition, anytime you use your Alexa, you call out Alexa or Siri or whatever, what's happening over here? The system is taking in a chunk of audio, the length of which is known, maybe or maybe not. Maybe the audio is just coming in continuously, but then it has to analyze the entire audio before it takes a decision. You cannot decide right here that the word Siri has been spoken. You have to wait all the way to the end before something is decided. Or here's this is a perennial favorite. Those of you who follow Steelers football know that something like this happens every semester. They're spectacularly bad. They've been so for 10 years. The Steelers, meanwhile, continue to struggle to make stops on defense. They've allowed on average 30 points a game and have shown no signs of improving anytime soon. Now, which game is this speaking of? Is there any cue over here that it's speaking of, telling you which game this sentence is about? Really no, right? So is it football? Is it basketball? You'd have to analyze the entire sentence and make sense of everything that's spoken before you come to any kind of a decision. You can't do it part way, right? Or investment. You're following the stock market. The inputs are sequences of vectors. And after observing everything until today, you have to decide which stocks are worth investing in. So the inputs now are sequences of vectors. The output may be a scalar or a vector. We may decide, you may want to determine the worth of a single stock or of an entire collection of stocks. In any case, you have to analyze the entire trend, what has happened over time before you make any predictions. So these are all problems, classification and prediction problems, where this was a prediction problem, this was a classification problem, right? So these are all classification and prediction problems where you have to consider a sequence of inputs and you have to produce one or more outputs. Again, we've seen 2 different kinds of problems over here. Here, for instance, you just have to wait till the end of the sequence to decide whether this was football or basketball. But if you're analyzing the stock market, you have to make predictions every single day. So but then in every case, you have to analyze everything that you've seen so far before you take your decision. And this, of course, is a function, function estimation problem, function modeling problem, and neural networks can model functions. So obviously, this can be done with neural networks. Now, when we talk about how this whole thing is going to be done, I'm going to use a certain kind of visualization, a visual representation. So I want to introduce that first so that it doesn't cause any confusions. Now, here is an MLP. We've drawn the MLPs facing you front on with layer on top of layer on top of layer. If I rotate it, eventually, if I look at it sideways, it's going to look something like that. So each box over here represents an entire layer of neurons. Each arrow represents a complete connectivity from every neuron on the lower layer to every neuron in the upper layer. So this is not like a neuron to neuron connection. It's a complete connection of this kind. This would be the input here. Here there are 2 hidden layers and an output layer. So for example, if you had a network that looked at 2 vectors of this kind side by side to make its decisions, if I drew it sideways, this is what I would draw it as. Or if I had a network which performed this kind of action where you had 2 vectors, one of which went through an extra layer of processing, and then they all fed to the next. This network is going to be shown sideways in this manner. So is this visualization clear to everybody? Each of those arrows is a complete set of connections. It's not anything other than it's not a element to element connection, just to be very sure. So let's return to our problem. I want to make a stock market prediction, right? I want to make a prediction about what I think, how good I think a stock is, or what the value is going to be tomorrow. So, and this information must be based on trends, everything that has happened in the past. What kind of model have we encountered so far that would make such predictions? Anyone remember? It's a one-day convolution, right? A straight up convolution. This is exactly what we've been doing this for 2 weeks and your homework. So at each moment, you can just have a sliding predictor of this kind, which looks at the last few days. This is just a convolutional neural network applied to series data, the so-called time delay neural network. And at each time, this could just look at the current and the past few inputs and make its prediction, right? This is a finite response system. The output at any time, the prediction at any time, considers the current input and the past n inputs, which means that something that happens today is going to influence your predictions for the next n days, but then when you get past the nth day, there is no more influence. So the response is finite. For example, if something were to happen at time t, as you make predictions on day t, this will influence your prediction on t plus 1, on t plus 2, and t plus 3, and so on. It will continue to influence predictions. But then if your model is looking at the past 3 inputs, on t plus 4, what happened on t is going to have no more influence on the output. So you're going to be making predictions past or based on short-term trends. Now, if you want to consider more of the past, then what would you do? You can increase the window, right? And so the longer the window is, the more of the past you would be considering, which is what you've done in both homework 1 and homework 2. So here's the problem. This is the stock market again. This is a typical seasonal pattern of relative rally in the stock market into Thanksgiving. What you'll find is that as you watch the stock market, there are daily trends. Things are either increasing or decreasing. There are weekly trends. Things happen over the weekend. There are monthly trends. People buy stuff when they get their paychecks. There are seasonal trends. Things happen by season. There are annual trends. Every Thanksgiving, something happens. Every Christmas, something happens, right? So these trends also inform, meaning if you want to make a prediction about what the market is going to be like next Thanksgiving, you want to look at what happened in the past Thanksgiving and the Thanksgiving before that and the Thanksgiving before that, right? So this is, now the thing is, these longer term trends probably have less of an influence than shorter term trends. If the economy is in the doldrums today, the fact that everybody was out in the market last Thanksgiving is not as informative as the fact that nobody really has a paycheck today, right? But that does carry information because you realize that something happens every Thanksgiving. So you have this effect where as you go further back in time, the effect is weaker and weaker, but you do have all of these very long-term trends. And so what we want is an infinite response system. Something that happens today should be able to influence your predictions all the way into the future, possibly with decaying influence. And that means you want a yt to be a function, the yt to be a function of xt, t minus 1, all the way back to t minus infinity. And this mechanism clearly is not going to work because you're not going to be sticking your taps all the way back to infinity, right? So I believe first we have our first poll. All right, 10 seconds. Does anybody on Zoom want to take the first question?
True.
Anyone on Zoom? Has anybody
True.
replied? True. Okay.
True.
And somebody here want to take the second question? False, right? Okay. So convolutional neural networks are finite response system, and input at time t affects the output for a very brief period of time. That's basically what we've seen. What we want is an infinite response system. So how can we compose an infinite response system? Here's what we can do. I can just feed the past prediction back into the system. If I feed the past prediction back into the system, then I can just say yt is a function of xt and yt minus 1. Of course, in order to do this, to make the prediction at time 0, I will need to a definition of y of minus 1. But once I do this, what happens? Anytime I have an input, I have a prediction at the next time instant, regardless of whether there's any further input or not, my prediction at this time goes back in, and that causes a prediction. And so now something that happens at time 0 causes the output to continue to be computed for the rest of time. So a single input influences the output for the rest of time. A function like this, if I were to model it with a neural network, is what is called a Knox network, or a nonlinear autoregressive network with exogenous inputs. I'm not sure where the nomenclature came from, so I'm not going to explain it, but that's what it's called. The output now carries the information about the entire past, because the manner in which you're passing the information about the past back into the system is through yt minus 1. And so if you have a Knox network with recursion from the output, it's going to operate something like this. At time t, you have the current input and the previous output coming back in. And that causes the current output to be computed. And then at the next time, this yt and the next input go in, and it causes the next output to be computed. And so on, all the way down the chain. So this is how your computations are being performed. If I were to plot all of the computations, this is what it looks like. And this is, in this figure, every column is identical to every other column, right? And so if I had an output over here, input over here, that's going to follow this chain of arrows and eventually cause an output here as well. And in fact, it's going to continue generating outputs for the rest of time. So you can see how this is an infinite response system. Now here, of course, I've drawn the output as a separate block. Just to simplify the picture, I can say that, the output layers, whatever the output layer computes goes out to the world, but also goes down to the next instant of the network. But when I plot it like this just looks like a very deep multi-layer perceptron with, what kind of multi-layer perceptron is it? So it has shared parameters, correct? Why do I have sharing? Every column is identical to every other column. And so it just looks like an MLP where I get inputs at various layers going in, and then MLP itself is arbitrarily deep. So you can think of it also like that. Now, again, an input at time t is going to generate outputs forever. I can extend this model and say that at any time t, you're looking not just at the current input, but the current and past few inputs and the current and past few outputs as well. So this is a generalized Knox network. This is an LK order Knox network, which looks at the L previous inputs and the K previous outputs. So these networks are actually were very popular for the longest amount of time. They're used to model time series, weather, stock markets, as alternate system models and tracking systems, any phenomenon with a distinct innovations that drives an output. Like something happens in the world, it's changing the output. The key thing over here is that when I write the function for the network, the memory at any time is obtained through the previous outputs. So the memory about what has been computed so far is not stored inside the network. The memory is in this external variable, which is outside, which has been thrown out into the world, the output. And you're grabbing that and feeding it back into the network in order to compute it, in order to refer to past computations. So we can try to make this memory more explicit. And if I want to make this memory more explicit, I want to introduce something inside the network that retains memory. The way I would do it, I can now define the initial ways in which this was done was through the introduction of an extra unit called a memory unit, a memory variable, which computed some function of past hidden states, inputs, outputs, whatever. And this memory unit was what carried information about everything that has happened in the past. And then at time t, when you computed the hidden states, you just used not only the current input, but also what was in memory. And the output was computed based on the hidden states. So these were sort of memory neuron networks, which actually retain information about past processing in the form of a memory unit. There were a couple of different formalisms proposed. One was the so-called Jordan network. Now, when we showed this little Knox network with a one-step memory, we just looked at the previous output that was looking at only one output. Now, clearly, it's reasonable to assume that all past outputs carried some information about the past. And so in a Jordan network, you actually had this memory unit over here, which simply maintained a running average of all of the past outputs. And this memory unit fed into the hidden state at the next time. This has a fixed structure. So the memory unit at any time computes mu times the previous memory plus 1 or 1 minus mu times the current output. So there's nothing to learn. The manner in which the memory updates itself is not learned, it's fixed. Secondly, the whole thing was treated as fixed. So when the training was performed, you'd have gradients traveling past here, going back here, and then the gradients would actually stop right at those blue units. There was no further propagation of gradients through the backwards at any point. So what this meant was that if you had a chain of this kind and you made a prediction error over here, this column was the only column where the corrections were made. But then you can imagine that errors are cumulative, right? So what is likely to happen is that something that happens here doesn't directly cause you to make errors in all of these layers and all of these time instants, but they sort of accumulate and eventually triggers an error 20 time steps out. This is not accounted for. Something that happens 20 time steps out only makes corrections out there 20 time steps out, and that error is not propagated backwards because during training, you're assuming that no gradients go past this blue block. The other network that was looked at, the other kind of model that was proposed was the Elman network. In the Elman network, you actually use the hidden state itself as the memory unit. So you just copied it over. And so the hidden state was cloned and retained. And this was used as input at the next time instant. So again, now you have an internal memory unit, but the internal memory unit is simply a copy of the hidden state, which is just directly passed forward. So this was 1990. Now, again, over here, this weight, this black arrow could be learned. But then when you're propagating errors backwards, each column, yes, Nate?
I'm just trying to make sure I understood the Jordan network correctly. Is the issue that essentially by fixing the memory structure, if the past proves to be like a poor guide to the future, there's no correction for that.
There's no correction for that, okay. Right?
So if the past stops being predictive, it keeps taking.
During when you're training, right? So.
Okay, thank you.
Yeah, and you have the same problem here as well. Once again, in the L1 networks, when we are performing back propagation, you'd be basically chopping the columns up and you'd be propagating gradients back to these blue boxes, and they would not propagate backwards. So any error that happened at any time made local corrections there. Of course, because it's a shared parameter network, those corrections are shared everywhere, but they are not reflective of what really happens, because the errors might have accumulated and triggered something way down the line, and that's not accounted for. So in the story so far, in time series analysis, models must look at past inputs along with current input. Looking at a finite horizon of past inputs gives us a convolutional network. We've seen this. We want to look at the infinite past, and this needs recursion, where variables within the model itself are fed back and update themselves. Now, Knox network recurs by feeding back the output to the input, and they may feed back a finite horizon, or just one output, or a finite horizon of outputs. But this was not a truly recurrent network, in that actually the Knox network was recurrent. The output goes back. But then these so-called simple recurrent networks, Jordan networks and Elman networks, actually have an internal memory unit. Jordan networks maintain a running average of past outputs in a memory unit. Elman networks store hidden unit values for one time instant in a context unit, which is your memory unit. Now, these models were called partially recurrent or simple networks because, as I mentioned, when you perform back propagation, the gradients did not propagate beyond one instant of time. They were blocked at the memory units in Jordan networks, or blocked at the context unit in Elman networks. 10 seconds, guys. Does anybody on Zoom want to take the first problem? Anyone on Zoom?
False.
Okay, and second thing song, what's the second one? True. Okay, the first one, memory neurons do not have true, models do not have true recurrence because the gradients are blocked. They dedicate neurons specifically to store past history. True or false? Obviously, this is true. Now, but all of this already gives us some clues. Yes, Ishan.
So, what's the benefit of introducing memory units in the last evolution?
So basically, the whole idea was that you're storing all the information in just an external variable, which is not inside the network itself. So the flexibility that you have is very limited, right? Now, once you actually begin introducing something inside, you have a lot more flexibility. Also, this ability to propagate errors backwards ends up being limited in all of those. Yeah.
Could you please reiterate why gradients are blocked in a memory unit?
So over here, basically, when they're performing back propagation, they stop here. So there's no derivation there. There are no derivatives. You assume that the derivative of this guy with respect to this one is zero, basically.
Okay, I see. Are there any ways that we could factor memory units and hidden units together?
That's what we're going to be looking at, right? So the obvious answer over here is, if I'm cloning this one, why bother to clone it? Make it the same thing, right? And that's what our infinite response of the state space models, which are what we now call recurrent neural networks, are all about. Here, now we have hidden states, which are a function of not just the current input, but also the previous hidden state. And the output is a function of the hidden state. So HT over here is the state of the network. You can think of this as a state space model. HT is a state and yt is the output. So the state of the system is a function at any time is a function of the state at the previous time and the current input. The output is a function only of the state. Of course, again, in order to be able to compute the state at time 0, you need hf minus 1 to be specified. That's an extra specification you require. But once you do this, you have true recurrence, because the variable that stores information about the past is an integral component of the network that is itself being updated. So this is a fully recurrent, or just a fully recurrent neural network, or these days nobody says fully, it's a recurrent neural network. So here's what it would look like. The computation at any time is going to look like this block on top. You have the hidden state ht, which is computed from the current input xt, and ht minus 1, and yt, which is the output, is computed only from the hidden state itself. So if you were to look at the computation across time, here's what it would look like. At time t0, you need hf minus 1 to be specified, of course. Again, this is something important. And then you'd have the initial input, and that's going to cause yt to be predicted. But then you're computing the h of 0, which is the hidden state at time 0. At time 1, the hidden state value is computed from the hidden state at time 0 and the current input, and then those are used to compute the output, and so on. The whole thing is recurrent. And now, once again, you can just follow the arrows to see that if something influences the network at time 0, that's going to influence the hidden state here, which is going to cause influences all the way here and cause the output to change way down the line. So the influence of an input at any time lasts forever. Also, you can see that because this whole thing is one long chain, and you can assume that gradients are actually propagated through every possible arrow. It means that if something over here caused the output to change here, and the outputs were okay in all of these intermediate times for whatever reason, that the peculiarities of your network, that would nevertheless cause these guys to be changed as well, because you're going to have derivatives that would tell me that a small perturbation over here would have caused a significant perturbation out there that caused the output to change. So the ability to propagate errors backwards all the way through time also exists. So here's the entire model. You have a hidden state ht, which is a function of the input at the current time, and the hidden state at time t minus 1. That's a state, and the output is a function of the state y is g of ht. So h is the state of the network, and y is the output. Although I've just written ht as a simple little block, in reality, ht can be arbitrarily complex. So for example, if I look into ht, that might be this green block. I may have several components within ht itself. It could in fact be a many-layered network. So if I think of ht as just having being modeled by a single hidden layer, then the network would look something like this. It's just got one hidden layer, and the hidden layers are recurrent, and something that happens at time 0 influences the output forever. On the other hand, my hidden state could actually be a 2-layer network, in which case I'd have a network of this kind. And of course, I would need to initialize the hidden state values at time minus 1 for both layers for this to work, right? And of course, there's no restriction on how the hidden state is composed. So I could have connections of this kind, and nothing stopping me, right? This is still falling within the same formalism. I have a hidden state, which has 2 layers, and you have their values at time minus 1 must be specified. And these computations are recurrent. The hidden state at any time is influencing the hidden state of the next time, and the next time, and the next time. And the input at any time is going to influence the output forever. So you can have something even more complex. And this too satisfies the model that we just had, that at any time you have a hidden state. And if I look at the hidden state at time t, the first layer is only getting an input from every layer at the previous time. So is the second layer, except that within the layer, of course, higher layers get within the time instant, of course, higher layers get their inputs from lower layers. So all of these complexities are encompassed within this simple model. So this is only looking at recurrence, which is considering one instant in the past. You can generalize this to say these models look at multiple time instants in the past. Nothing stopping you, right? And that you would expect as a more flexible model and captures second order recurrences within the state itself. But of course, in order to do, and that recurrence could be at any layer. Again, all of these variables are permitted within this model. And of course, if I'm having a hidden state look at two past values, then at time t0, I need the hidden state value at both time -1 and time -2 to be specified. So these are initializations that will be required just for this model to work. But besides that, this higher order generalizations are also permitted, right? And once again, when I draw the network, I want you to remember that every column is identical to every other column. Basically, this is showing the computation that happens through time as you make predictions. Question, Nate?
Yeah, I have two. The first is when you say it looks at one instance in the past, I thought all of the past was affecting this.
Yes.
Not looking at
The
specific.
hidden state HT is looking at HT -1. So yes, the entire past has influenced HT -1, but it's explicitly considering just HT -1. You could explicitly consider two of these values, and that's going to be a somewhat more complex model.
So that would be like if you were doing the stock market prediction, you could explicitly encode, look at this time last year to put greater emphasis because you think that it's going to have more influence.
Yes.
Okay.
Or you can say, look at it last week or something of that kind.
Okay. And then my second question, this looks very much to me like building up layers in a convolutional neural network. Does a multi-layer recurrence like this result in building up like patterns about the past?
You would expect that to happen, except of course you have the recurrence, right? So the idea is that as you add more layers, you're still sort of building hierarchically more complex patterns.
Okay. Cool. Thanks.
Now, in general, when we work with these models, we're going to look at models like these. One-step recurrence, very simple layer structure. But you have to keep in mind that this is not the only thing that's possible. All of these other things are possible as well, right? Now, when you look at textbooks and papers, then the visualization is usually given in this manner, which is very confusing, at least to me. And they show me this arrow, which seems to tell me that the recurrent state is looking at itself. It looks like a loopy computation. It is not. So you can have all of these different kinds of representations. What do they actually represent? This figure over here represents something of this kind. It just means that the hidden state is looking at itself from one time instant in the past. And so the entire computation is as follows here, right? This figure over here again says that the hidden state has two layers, and each layer is looking at itself one time instant in the past. So each column, as you can see, is basically this figure over here, except that the loopy arrows are representing representing recurrence, and not self whatever, looking back at itself, right? It's not introspective. And so something of this kind is going to have this structure where anything that's shown with a loop is basically representing a variable that's looking at its own value one time step in the past. So Taeyong, you need to go wash your face. It's okay. It's 8:30 in the morning. I know. I'm sleepy too. So just go wash your face. Right? Happens to all of us. Trust me, if I were not up there, I'd be sleeping. Right? Sometimes I'm up there and sleeping. Anyway. So what do the computations look like? So here is the computation for the simple one-layer hidden network. Now at any time t, of course, the hidden state value at time -1 has been specified. At any time t, you first compute an affine value. So I'm looking at the computation for the hidden state itself. I first compute an affine value, which is an affine function of the input at that time. That is this guy, which is a linear combination of the input components at that time and the hidden states at the previous time and the bias. So it's an affine function of the input at time t, the hidden state at time t minus 1, and a bias. And that is put through some kind of an activation, which, as we will see in the next class, is typically a tan H for some very valid reasons. And then the output layer, of course, doesn't have any recurrence. So it first computes an affine value, which is an affine function of the hidden state components at the same time, which is put through the output activation. So if I were to write this in vector format, this is what it's going to look like. Xt is the current input vector. And so the hidden state at time t is some weight matrix times xt plus some other weight matrix times h at t minus 1, the hidden state itself, the hidden state vector itself at time t minus 1, and a bias. Is that a question?
Yeah.
Yeah.
I was gonna ask, with the way we're writing it, it seems like we're gonna need infinite space to store the neural network in a sense.
So not really, because you only have to store the parameters for one column, right? But as you compute the amount of memory, the data you would have to store, if you want to store our intermediate variables, is going to be proportional to the length of the input. Right? And so again, the output layer has got this computation. It has a weight matrix with which the hidden state vector at that time is multiplied and a bias. So there are two kinds of weights over here. These guys, these weights are going down the arrow at the same time. So they are current weights. They are not looking at any other time, right? These are the weights that are looking at the same value at the previous time. So they represent recurrence. These are recurrent weights. They're the recurrent weights. And so you have two sets of weights, the current weights and the recurrent weights. And all of these contribute to the computation of the affine term to which the activation is applied. But this is only for the recurrent states. Obviously, in this model, the output layer has no recurrence, and so it doesn't have any recurrent weights. Now, so these are the current weights over here, the W. They represent the connection going down. And these W11, the superscript 11 says the layer 1 is looking at layer 1 from the previous time instant. And that represents the recurrent weights. Okay? Is this making sense to everybody? What did I managed to fly. It's very easy to go back to make mistakes and takes a lot of time to fix them. Okay. So this one makes sense to everybody, right? Now, just to be clear, please take a note of the notation. W superscript 1 represents the weights to layer 1. W superscript 2 represents the weights to layer 2. W11 represents a recurrence from layer 1 to layer 1. I'm going to be using this notation later, so just please note, okay? So over here again, when I have something of this kind, you have similar equations, right? So first, the first recurrent hidden layer is going to compute an affine function of the input, this one, the input, and the hidden layer itself at previous time t, the previous time t minus 1, and a bias, and then an activation is applied to it. The second hidden layer is now computing an affine function of the output of the first hidden layer at the same time, and the recurrent and the second hidden layer at the previous time, and the bias. And this is what the activation is being applied to. And the output layer is only looking at an affine function of the second hidden state at the current time, second layer, the second hidden layer at the current time, and this bias. So if I were to write this in vector form, which is always much cleaner to write, as we know, this is what it would look like. H1 at any time is being computed over an affine term, which is W1 times xt plus W11 times ht minus 1 plus the bias to which an activation is applied. The second hidden layer is W2, yeah, because the second layer, right, at time t plus W22 at times the hidden layer at time t minus 1 plus the bias to which some activation is applied. And the output is some W3 times H2 plus the bias to which some activation is applied. So you see how the whole thing works. Of course, if I make it more complex, something like this, the same kind of logic holds. Now, I actually have a weight associated with this guy. So this one, for instance, has a weight associated with the hidden state of the previous layer, the hidden state at the previous time, and the input. So there are 3 sets of weights to which would be required to compute the affine value on which the activation is applied. So this thing can be made arbitrarily complex. Now the kinds of recurrence that you can see can be many. So you can just have a one-to-one recurrence, which is basically no recurrence. An input that occurs at this time computes a hidden value at this time, which computes an output. This is just your standard MLP. You could have something of the second kind, one-to-many, where I give the network a single trigger and then it continues to produce an entire sequence of outputs. So it doesn't have many outputs, it just has an instantaneous input and it produces a sequence of outputs. Or, so this, for example, could be sequence generation. I'm generating text, I give it some input, it produces an entire sentence. Alternately, you can have a sequence of inputs and a single output is produced. So I give it a sequence of spectral vectors. At the end of it, it says, oh, this was the word hello. So the output comes at the end. And oh my, why does that happen, right? Okay. So you can also have this many-to-many, a delayed sequence where you have an entire sequence of inputs, and then when the last input has come in, it produces a sequence of outputs. This, for example, would be required in machine translation. You have to see the entire English before you can produce the entire French. And then, of course, the many-to-many. This was the stock market example that we saw. Every day you see everything that has happened in the past and make an instantaneous prediction. So of these, this is probably the most generic. It subsumes all the rest. So we'll spend a lot more talking about this one. So the story so far, just adding our current statements. State space models retain information about the past through recurrent hidden states. So these are what are called fully recurrent networks. In all of these, you must specify the hidden state value at time 0, hf minus 1. Where did that hf minus 1 come from? Nobody gave it to you, so this can either be set to some 0 or this can in fact be learned to be optimal. So in that case, hf minus 1 is also a learnable parameter. All of the h minus 1s are learnable parameters. And these models actually enable current errors to update parameters going way back into the past. Now, how do you train this network? Questions, anyone? Yeah.
On the variants of elements, do we also always learn like one column, or like do we learn multiple columns?
So that's just one column because all of them are identical, right? So you're going to get derivatives down all of the columns, but then eventually it's a shared parameter network. Every column is identical to every other column.
But then you have these output columns as well. So you learn like one input and one output column.
So meaning?
So like you have outputs in the variants. You have many-to-many, right?
So over here, from many to many, you just learn one column and you're done.
Okay.
Right? Because all of these are identical. These things, we can think of it. So the reason I said this was a most generic setting is that you can think of this as a generalization of this, as a special case of this one where you're sort of ignoring this portion and ignoring this portion, right? But then there's more to it than that, and we'll get to that in the coming classes. But that's a good question, right? Because it does bear on what we will be talking about in the subsequent classes. Any other questions? Anything on Zoom? No questions on Zoom? For some reason, people on Zoom understand what I'm talking about much better than people in the classroom. So I don't know why that is. Maybe just the proximity to the screen. But anyway, how do you train such a network? Now, we're going to look at it through the lens of this guy. for the reason you don't have your name. Yeah, I can't read it when it's folded. Okay, so Durvesh. So Durvesh, this goes back to your question, right? Hold it up when you talk to me so that I know who I'm speaking to. I'm sorry, but so this one is what we're going to be looking at, because as I said, I can look at all of these models as special instances of that one where we're sort of ignoring some components, right? This is like saying I'm setting the inputs here to 0. This is like saying I'm throwing away all of these outputs. So let's look at this model. Now, in this model, what happens? I have a sequence of inputs coming in. I have a sequence of predictions being made at each time. So this means that when I'm presenting a training sample for this model to be learned, each sample must have a sequence of inputs and must have a desired sequence of outputs, because you must have the desired version of everything that I'm already computing, correct? And so this means that your training sample is going to be x0 through xt and d0 through dt, where the d's are the desired output at each time. That making sense? Right? And this matters. Why? Because when you train the network, you're going to be training the network to minimize the error between not a desired single output, but the desired sequence of outputs and the actual sequence of outputs. And this is a significant factor that's going to come back and bite us in the rear again and again. Now, so when I'm training the network, here's what the unrolled computation looks like. It's just a giant shared parameter neural network. All columns are identical and share parameters. Every column looks like every other column, right? Network parameters can be trained via gradient descent or its variance using shared parameter gradient descent rules. Now, gradient computation requires a forward pass and back propagation and pooling of gradients. Now, it needs a forward pass because you need to have all the intermediate values. We know this. We need backward pass because gradients, as we saw, must be computed from the end and go back to the beginning. And as always, why do we need to go from the end to the beginning? This is just why is there never a chalk here? Is there anything that resembles a chalk somewhere around here? So when I got something, thank you. So when you have any computation of this kind, and I'm just showing a very simplified influence model sort of structure, then if I want to compute how much this one influences this one, we have to work our way backwards. The way we do it is how much will perturbing this variable change this one, right? And then only when you have that, you can go back and say, oh, and how much does perturbing this variable change this? Because then I can chain them up and tell you how much perturbing this variable is going to change this output. So the derivation has to go backward. You cannot compute your derivatives forward. The error is at the end. It has to be moved backwards, right? So you're going to have to perform gradient computation going backwards, back propagation from the final time instant, working your way backwards all the way to the beginning. Now, so for training the network, for each training input in the forward pass, you pass the entire data sequence through the network to generate outputs. I have some pseudocode over here. This is just, for your reference, I'm going through time, and I can do this sequentially one step at a time. I'm assuming hf minus 1 is given. Just for simplicity, I'm going to call this the 0th hidden layer, just for notational simplicity. Then you go through the layers, and at each layer, you compute an affine value, which is an affine function of the same layer at the previous time. Actually, the same layer at the previous time, the hidden value at the lower layer at the same time. So this htl minus 1, ht minus 1l. Observe the flipping of the indices and the bias, and then you apply an activation, which is typically a tan H. And then, of course, for the final layer, you're just computing an affine function of the output of the final hidden layer and applying an activation. So again, this is key. The affine value at any time is an affine function of the hidden state at the same time, at the lower layer at the same time, and also the hidden state at the same layer at the previous time, right? So now when I'm computing gradients, when I perform the forward computation using this little operation going left to right, bottom to top, I'm going to now compute my gradients going all the way back from the end, top to bottom, right to left. Right. This is, and because we are computing the gradients going starting from the end and working our way backwards, we are going backwards through time. And for this reason, this is called BPTT, or back propagation through time. It's still back propagation, but then you're going backwards through time. Now, just for the purpose of illustration, I'm not going to draw a horizontal arrow like this. I'm going to make it go down here from the bottom, just to show you that all of them are going into the same place. I don't want this box with arrows going in from different directions to give you the kind of idea that there are inputs coming in at different levels. So yes.
Just a quick question here. So when we are doing the backpropagation here, the cap T is already a fixed constant, right?
Yes, once the input is, it's not constant, but any given input is going to be of a specific length.
Oh, I see. Okay, sure.
Right, and so that input is going to be given, right?
So it's always been considered as finite because we already know that the time is just the length of the input.
The length of the input, that's a training input.
Sure.
Yeah. During operation, you don't have to terminate it, but your training data is terminated, right? I mean, there are engineering solutions for training, learning from streaming data and such like, but it's convenient to think of it in these terms. This is the simplest way. So now I'm going to redraw the figure like this. So this figure, is this figure confusing anybody? I should hope not, right? Now, okay. Once you pass the input through the network, it's computing an output at every time. So you would have one output at each time in this manner. It's a sequence of outputs. There's also a desired output at each time, what you want the network to actually compute, and that too is a sequence. And so now you'll be computing a divergence function, but the divergence is going to be between the sequence of outputs and the sequence of desired outputs. Now, I want you to keep this in mind and be very clear about this. The divergence that we are computing is not just the divergence here, the error here, plus the error here, plus the error here. No, it is not that. When you're comparing two sequences, there are many ways of comparing sequences. For example, if I were performing speech recognition, I have an input, I have a desired output, which is, has anybody watched, Good, Bad, Ugly, where there's some guy lying in a bathtub going into a long 15, 30-second harangue at the bad guy, and the bad guy says, when you want to shoot, shoot, and kills him. So if you compare the two sentences, one of them is like 60 words long and the other is 5 words. So you don't have a one-to-one correspondence between the two. It's not like you can actually make comparisons, say this word is off, this word is right, this word is wrong. There's something more. So you're computing sequences, and there's no clear definitive way of saying that sequences can be compared. And so as a result, you should think of this as saying this is some function which considers two sequences and produces an output. This is important. And so this divergence is not the sum of divergences at individual times unless you explicitly define it that way. By default, it's an error between two sequences which can be defined in many different ways, and that's open to interpretation. There's a specific instance of it where the total error is going to be the sum of the errors at individual instances. As it turns out, that's probably the easiest one for us to deal with. So very often we take more complex error functions and try to map them onto something of this kind and work off of that. But if that is simply not feasible, you're going to have to work out some way of dealing with this more complex divergence function which compares two sequences. So notation, here's what, but when you have a divergence of this kind, you're still going to have one requirement, and this is a challenge. what do we need the divergence to be? What is the characteristic that the divergence function must have? It must be differentiable with respect to what? It must be differentiable with respect to every one of these y's. Otherwise, there's no question of propagating derivatives backwards. So regardless of what the derivative divergence function is, it must be differentiable with respect to every single output. Let's assume that will hold. So then here's what the network is going to do. You're going to have, you have the forward pass, all of these variables are computed. So you passed x0 through x3, xt through the network. And at each time t, the output produced, the network produced an output yt. And specifically, if I want to represent components, I'm going to have a subscript y underscore it, which is the ith component of the output at time t. Now, just some notation again. Here I just have a single hidden state. You can generalize this to any number of hidden states. I have an affine value being computed at each neuron. And then there's an activation function being applied to this affine value. So the H represents the hidden state after the activation has been applied, the Z for the hidden state, and the Z superscript 1 represents the affine value at the hidden layer before the activation function has been applied. Similarly, at the output layer, I have Z superscript 2 that represents the affine value before the output activation has been applied, and Y is the result of applying the output activation to the second affine term Z2. Notation clear to everybody? Okay. Now, again, more notation because I have one hidden layer and an output layer. So I'm going to have W superscript 1 as the current weight going from the green box to the input, the purple box. W superscript 1 is the recurrent weight going from the green box to the green box at the previous time. And that's the weight associated with this curly connection. And then W2 is the set, represents the set of weights going from the hidden state to the output layer. So the subscripts over there represent the components. So the subscript ij would represent a weight. This W11 ij is a weight connecting the ith hidden state value at time t to the jth hidden state at time t plus 1. Right, because this is recurrence for this one. Anyway, so how does the gradient computation happen? Again, I'm going to assume that this divergence function is somehow differentiable and that I can compute the derivative of the divergence with respect to every one of these outputs. So I can compute the gradient of the divergence with the output at any time. Or more explicitly, I must be able to compute the partial derivative of the divergence with respect to every component of every output. This is an assumption we will make. This is going to be the most challenging bit of dealing with recurrent networks because very often the divergences that we will have may not be differentiable, right? So now again, the divergence is actually a function of all of these outputs. We're simply going to assume that it's differentiable with respect to all of these outputs. And obviously it makes sense that it must be. If I perturb any one, the divergence should change. Or and that we can actually compute these derivatives for all the outputs and all components of all outputs. Now let's assume we have this. I'm going to make another special, consider a special case because this we will deal with. The special case of a divergence is one where the global divergence is simply the sum of the divergences at individual time instance. This would be a case where the desired output has a one-to-one correspondence with the actual output. This may not always be the case. Like in speech recognition or machine translation, your network outputs 50 words. Your desired output is 20. There is no one-to-one correspondence. But we're going to assume that there is a one-to-one correspondence between the desired output and the target output, like in the stock market prediction case. In that case, I can just compute a divergence at each time and sum the lot of them. And then I can say that my overall divergence is the sum of the divergences at individual times. In that case, of course, if I want to compute the partial derivative of the divergence with respect to any given output, it's sufficient for me to compute the derivative of the divergence at that time with respect to the output, simply because the global divergence is a sum of all of these local divergences. But this is a special case. We cannot assume this to be true all the time. The more generic assumption is this one, that we have some divergence function which is somehow magically differentiable with respect to all of the outputs, and that we have a way of computing it. Now, assuming that I have a way of computing it, how can I perform my backpropagation? My backpropagation has to start at the end, as I mentioned. So the first thing I will assume is that I have the derivative of the divergence with respect to all the components of yt. Then, once I have the derivatives of the divergence with respect to, or the gradient of the divergence with respect to yt, I'm propagating things backwards, right? So I'm going to propagate things backwards through the output activation. And when I propagate it backward through the output activation, assuming I have this term, the derivative of the divergence with respect to yt, what do I need to do to get the derivative with respect to the affine value at the output? Someone say it aloud. Chain rule. Can you say that aloud? So everybody, you have to be heard in Africa. Chain rule, right? So what would the actual derivative rule be? This is simply going to be the derivative of the divergence with respect to yt times the derivative of yt with respect to z2 at t. And what is this? What is this term over here? Anyone, guys, what is that term? So there's the J word. What's the J word? Jacobian, right? That's the Jacobian of the activation at this time. So I have the rule, the vector format of the equation. You can skip the scalar format. This is just for reference. You have the derivative of the divergence with respect to yt times the Jacobian of the activation will give you the derivative of the divergence with respect to z2. That's easy. Next, I can use that to compute the derivative of the divergence with respect to the hidden layer output. And how do I do that? Again, I multiply the derivative here, which is the derivative with respect to z2, by the derivative of z2 with respect to h. And what was that? That was just the weight matrix, right? So I'm just multiplying the derivative of the divergence with respect to z2 by the weight matrix. That gives me the derivative here. What next do I need to compute? Derivatives over here. Someone? Someone mentioned something. What is the next derivative term? Guys, wake up. Pardon me? The derivative with respect to the weight matrix. So Anusha, can you give me the answer? What is the derivative going to be? The derivative with respect to the weight matrix over here, that's W2, correct? What would it be? Anyone? We've done this only like 5 times or 6 times in class.
It'll be, it's like derivative, it'll be like the derivative of like the divergence of frequency times like the orange one.
Okay, you gave me a visual answer. It's the derivative of divergence with respect to z times the orange one. Is that going to be the correct shape? That would be a scalar, right? Because the derivative with respect to z is a row vector. The orange is a column vector. So you're going to be orange one times the derivative with respect to z, right? That's going to give you a weight matrix. Should that have been so hard? Can everybody say no for me, please? No. Thank you. So at least I need some enthusiasm with the negatives. Okay, so that's easy to compute. It's just h of t times the derivative of the divergence with respect to z2, right? But I'm still going to, now, what would I compute next? I already have the derivative with respect to h, which is because that's what I computed here. I mean, here, right? And I have the derivative with respect to the weights. What do I compute next? It's back propagation, guys. Pardon? Can you say that aloud? So I'm going down. How can I compute the derivative with respect to yt minus 1 from here? What I'm here, where the location that's being shown by the arrow. What is the next thing I'd compute? I'm back propagating. I have to go down and compute the derivative with respect to the z, right? And that is going to be obtained by multiplying the derivative with respect to h by the derivative of h with respect to z. And what is that again? Jacobian. Okay, everybody say Jacobian aloud. You're sleeping. 1, 2, 3. Go ahead. Thank you. Right. So this is easy. I can compute this derivative here. Right. This is the Jacobian. And then I'm out here. What is the next thing? I'm continuing down first. Right. What is the next thing I would compute? The derivative with respect to the weights, which is going to be xt times the derivative with respect to z. Right? So xt is a column vector, the derivative with respect to z is a row vector, so the result is going to be a matrix. If you're ever confused about the order, you just have to consider the shapes and you will get the answer. Right? There's one more parameter to be computed. What is that? So this, right? What is the derivative with respect to this recurrent weight? The derivative with respect to the recurrent weight is going to be ht minus 1 times the derivative with respect to z1t, correct? This making sense to everybody? Yes. Right, okay. This was the easy bit. And then I go to the next time, and the next time again, I assume that I have the derivative of the divergence with respect to yt minus 1. I can pass that down and compute the derivative with respect to z2t by just multiplying it by the Jacobian of the activation here. So that's easy. And then I can compute the derivative with respect to ht minus 1, but then here is the thing. Ht minus 1 has gone up to yt, that's also gone right to ht, right? So now the derivative with respect to ht minus 1 actually has two terms being summed. One is the line component that came straight down, which is the derivative with respect to z2 times w2 plus the derivative with respect to z1t, right, times the recurrent weight matrix. So everybody see where this came from, right? This is not complex, but the fact that h is splitting out two ways means that two derivatives must be summed. Now, so this was one. Here's another modification. Now I can compute the derivative with respect to the weights for the red connection, correct? And when I compute the derivative with respect to the weights for the red connection, that's going to be again h2t or ht minus 1 or h of t minus 1 times the derivative with respect to z2 at time t minus 1, right? That's this guy. But then this weight is the same as the weight at the next column. So what do we know about the derivatives of shared parameters? What happens to them? They get added, right? And so what we had is that we already had a derivative of the divergence with respect to W2. We add to it this term, which is ht minus 1 times the derivative with respect to z2. We summed it. That making sense to everybody? Right. Then I can go further one step down and compute the derivative with respect to zt minus 1. Same formula as before. But then once again, when I compute the derivative over here, I'm going to be summing the derivative I got with the same term that I already had earlier. And so also for this recurrent weight, I'm going to be summing the derivative, which is going to be, ht minus 2 times the derivative with respect to z at t minus 1. That's this one. That is being summed with the derivative added to the derivative I got at the next time instant. And so now I can use this computation going backwards like so and work my way all the way to the back, where if necessary, I can also compute a derivative with respect to hf minus 1. Right? Any questions? So here is the complete set of equations. Initialize all derivatives to 0. I'm going to assume that I have the derivatives with respect to all the y's. Then from t down to 0, first you're going to be computing the derivative with respect to z2t over here at any time. Then you're going to be computing the derivative over here with h, which has two components, one coming vertically down, one coming from the future. And then you're going to be computing the derivative with respect to the z at the previous, one step down using the chain rule, where you post multiply the derivative with respect to h by the Jacobian. And then these are all the weights. At each time, in order to compute the derivative with respect to the weights, it's going to be the input times the derivative of the output, right? And that just keeps getting added incrementally to all of the terms that have already been computed. So we have some pseudocode for back propagation through time. I'll skip it to save some time. But this can be generalized to pretty much any architecture, this overall structure. Please go through the pseudocode because you are going to be answering things about it, if not in the quiz, in the homework. So there's a poll. We won't have time for poll 4. This one, I'm only going to give you 30 seconds for this one because we are out of time. Okay, 5 seconds, guys. Okay, does anyone on Zoom want to take question 1? Anybody?
False.
Nobody on Zoom wants to reply, right? False, okay. Someone here want to take question 2? Second one, right? So the first one is false. The divergence between the actual sequence of outputs and the desired sequence of outputs is between the actual and desired sequences of outputs and cannot always be decomposed into the sum of divergences at individual times. And now the over here you have to consider entire sequences, and you are not training over individual instances, samples, right? Now here's a very simple extension of this. When we spoke of this model, we were always speaking of computing left to right. But there are many situations where you have the entire input before you can make predict the entire output. Can someone give me an example of this? Machine translation, you have the entire input. You can go through it left to right. You can also go through it right to left, right? And as far as the computation is concerned, there's nothing favoring the one or the other. It's the same thing, whether you're looking at the world from this end to that end or from that end to this end, because the entire thing is there. Why choose the one? Why not do both? And so you have this idea that you can actually analyze the input both forward to backward, from front to back and back to front, or from 0 to t and back to t-1. So these are recurrent networks with both forward and backward recursion. Originally proposed 25 years ago in this brilliant paper by Shuster and Paliwal. So here's how the computation goes. Now clearly, I cannot be having a single recurrent network which looks at both the past and the future, because the future has not been computed if I'm going left to right, right? And so also, if I'm computing, if you think of it this way, if I'm computing right to left too, you don't have both the past and the future. It's complex. So how do you deal with it? You separate out the forward computation from the backward computation. That's the genius of this particular work. And the genius lies in the fact that realizing that is fact of realizing that you can separate these two blocks out into two separate networks. So within each block, you have a forward net, for which you define an initial hf minus 1. It takes the input and performs the recurrence going left to right. You also have a backward net for which you have an initial value h infinity defined. And then you start at the end and work your way backwards. And so this starts from this end and performs its computations backward. But now I have these two distinct computations, one performed left to right, the other performed right to left. I can combine the two to make it the output of the block. There are many ways of combining the two. I can add the two, or I can simply concatenate the two. Concatenation is probably the more easier way to visualize it. But the point is now the output of this block now is got the computation of both working causally from beginning to end and anti-causally from end to beginning. So in language, for example, it makes a lot of sense. If I'm trying, for instance, to perform part of speech tagging, the words that led up to this word tells me what this part of speech was, but how this influenced the future also tells me what this part of speech was. So you can imagine that this guy is looking at the previous words and this is looking at the future words, and together they will help me decide what my current word must be. And so the forward network processes the input from 0 to t. It only computes the hidden state values. The backward network processes the data in reverse time, end to beginning. Again, only the hidden state values. This is not the backward pass of backprop, to be very clear. This is a backward prediction, right? And then the two outputs are just connected, are combined typically through patching them together, because there's going to be one-to-one correspondence. And now, of course, you can have many such blocks. So what was just a single step recurrence, it can be a bidirectional recurrence. Your entire network could be a stack of such blocks. Or even so, within each block, each of the forward and backward networks could themselves be a multi-layered network. And there's nothing stopping you from doing that. The whole point of this is that you can think of forward predictions and backward predictions and combine the two, right? So I'll skip this poll, actually have this poll. This is an interesting one. We'll go a few minutes over, bear with me. This is going to be a 15-second poll. Anyone want to answer the question? False, right? Is clearly false, right? A stock trader cannot use a bidirectional network. Why? There is no future. You don't have the future. This is a very specific kind of problem. So now I have pseudocode for it. Here is a beautiful thing. I don't need to write two separate blocks of code. I'm writing a forward recurrence and a backward recurrence in the pseudocode. But a more convenient way can be to say, just write a recurrence. I use the same code twice. Once I use it, pass the input and going forward, then I flip the input and pass it to the same code with the backward parameters, and I perform the computation going backwards. Now, the key thing to remember over here is that these two components of the network have completely different sets of parameters. The parameters that you're going to be using making forward predictions are not the parameters that you would be using to make backwards predictions. So they're going to be very, very different, right? And so you'd have to pass the parameters in as well in order to make your predictions. Now, how does back propagation work? I'm going to go a couple of minutes over, bear with me. So in the forward pass within any block, it is going to pass both the forward and do the forward and the backward computations and patch the outputs. Now, suppose this guy computes a 20 component output. And let's say this guy computes a 30 component output, just I'm making the two different. Then the final output is going to be 50 components, correct? I have a 50 component vector, of which 20 came from the forward code, 30 came from the backward net. When I compute my derivatives backwards, how many components will the derivative have? 50, right? Of which the first 20 are going to have come from the forward, and the next 30 are going to have come from the backwards. So the derivatives can now be split, saying this portion of the derivative is due to the forward, and this portion of the derivative is due to the backward network, right? So here, if I have my forward net and my backward net, and this computes a 30 component vector at each time, this computes a 20 component vector at each time, these guys are going to give me, this is a 20 component vector, this is going to be a 30 component vector, this is going to be a net 50 component vector going out. When I'm coming backwards, I'll have a 50 component derivative. So this portion I can assign to this one, this portion I can assign to this one, right? So even the derivatives can be split going back. And that makes things very simple. So all I can do is to say that I can separate the gradient or the derivative over here into the portion that came from the forward network and the portion that came from the backward network. And so now I have the derivative of the divergence with respect to the outputs of the hidden layers at each time, right? So now I can now perform back propagation for this one, for the forward net from the rightmost end to the beginning. For the backward networks, where will I start back propagation from? From the beginning, right? Because it has to do in the reverse of computation. It has nothing to do with time. It's no longer back propagation through time. For that, it's forward propagation through time. And so for the backward network, you'd start computing the derivatives here and work your way backwards. So for the forward net, you'd have all of these derivatives. You can perform back propagation in this manner. For the backward net, you have all of these derivatives. You can compute the back propagation in this manner. And then finally, here's the bit. The forward net is also going to give you a derivative with respect to the inputs to the block. The backward net is also going to give you derivatives with respect to the inputs to the block. Suppose the dimensionality of the input to the block was, say, 20. What is the dimensionality of the derivatives with respect to the inputs that you get from the forward net? 20. What about the backward net? 20, right? And how would you combine the two to get the overall derivative with respect to the input? You would have to add them because the same input is going both places, right? And so you're going to be performing a summation, going back to compute the derivatives with respect to these. And then you can pass them on. Again, I'll stop here. We're out of time, but there's a very nice and clear pseudocode that explains the backward computation for the bidirectional network. Please take a look. So just to summation, just to summarize, bidirectional networks analyze data both ways, beginning to end and end to beginning to make predictions. In these networks, backprop must follow the chain of recursion and gradient pooling separately in forward and backward networks. So again, stop here. Thanks for your time. Well finished. We'll continue with this topic in the next class. Again, the next homework is already upon you. So just, if you've got a minute, a bit about the dates and times, just hang on a second. We've had a bit of a delay with our projects. The project proposals, as you will note, were due on some particular date, and that did not happen. Part of the reason being that we have an external component to the projects. We're dependent on external mentors, and that was slow. So that has slid by 4 days, which means that all of our entire schedule is going to require a little bit of adjustment. We'll make a post about this. The quizzes will not change, but our homework deadlines and the project deadlines will change a little bit. You do have a quiz this week, but we are giving you 4 extra days leading in. We will have a very easy quiz at the end of the break week. That's because we don't want you to get too comfortable during the break. You might just forget what it is to work hard nonstop, and that's not a good thing. So you'll have an easy quiz, but then the quiz is easy enough that you will be able to do it after you come back. We're nevertheless going to release it on Friday for those of you who don't want to be bothered with having to deal with quizzes when you come back. Right? So thank you.